Hi guys, welcome to our channel of Sciences and Mathematics. Today we're going to look at a topic in mathematics that goes by the name logarithms. Logarithms are very important because of course they assist us in solving algebraic expressions that have got powers, or that have got known variables that appear as powers. So in this case we're going to explore this concept of logarithms and the relationship between logarithms and indices to try and figure out how we can be able to work with problems, of course, with such a kind of variable. So without further ado, thank you and welcome. So as I've said, today's topic of discussion will be on logarithms. And in this case, I've defined logarithms. Of course, the different kinds of definitions or approaches on which we can be able to regard logarithms. But in this case, of course, a logarithm is a mirror image of an index. In one of our videos, when we are trying to talk about logarithms, logarithmic and logarithmic and exponential functions, we say that there's a relationship between indices and logarithms. And these are basically powers, of course, powers or exponents. We're going to see the difference between the two, or the relationship between the two through an illustration. So in that case, as I've said, a logarithm is a mirror image of an index. And suppose we have an index, or maybe a function that is given as n, which is a product of an exponent, which is b raised to power n. Then we can write this one. This is an exponential equation, and therefore we can write this one as a logarithm by stating that it's a log to base b m, which is equals n. So in this case, this relationship that exists between logarithms and indices, therefore this one now can be, of course, stated as the log of m to base b, which is equals to n. Of course, we have a function which is also another exponent, that is y is equals x raised to power n. Then this one, of course, can be rewritten still as n, which is the exponent, is equals log to base x of y. So we are trying to look at the relationship between logarithms and indices. But as we can see from this, still this one can be written as b raised to power n is equals n, therefore implying log to base b m, which is equals n. Therefore this will be the implication of that. So we're going to give a number of examples using numerical figures, or maybe the normal numerical figures, in order to illustrate this relationship between the two that we have talked about. So suppose we have a number like 1,000, 1,000. This one can be written as 10 to the power of 3 as an exponent. Therefore, we can say that from what we have stated, 3 is equals log to base 10 of 1,000. So that one can be written as that. Now suppose we have a decimal fraction like 0.01. Now this one is the same as 1 over 100, or just 1% as such. So this one can be written as 10 raised to negative 2. Therefore, in form of a logarithmic function, it can be written as this power, which is an exponent negative 2 base 10 of 0.01 is equals to. Therefore, these are basically the relationship that exists between logarithms and those exponential functions. Now, there are specific rules that are going to be used, especially the rules of indices, which are going to apply also to the rules of logarithms. But there's a specific procedure which we are going to use in order to apply these rules of indices whenever it comes to logarithms. So I'm going to just try to state these rules in a specific order so that we can be able to see the relationship between the two. So suppose we have a number that is log to base b over number x times y. So in this case, from indices, the laws of indices, this one will be log to base b of x plus log to base b of y. So in this case, whenever we have a product at this particular point, we can rewrite that one as a logarithm which is expressed in two parts, of course, which is the sum of the two. For example, we have log to base 10 of a product of 2 times 3. This one can be written as log to base 10 2 plus log to base 10 3. Therefore, the sum of those two logs will give us the product which is equivalent to that one. Now, suppose this is example number 1. Number 2, suppose we have a fraction that is log to base b of x over y. This is a division. Now, in that case, we are going to have log to base b x minus log to base b y. So for a division, we're going to have a difference or subtraction between the two logs, and that is the rule that is going to apply. Suppose we have an exponent just like the one that we have been given before as a logarithmic function. So we have log to base b of x raised to power m. So in this case, we're going to bring this part of the exponent there, and then we are going to have log to base b x. So this is a rule that is going to apply besides the first two rules that I've stated in order to try and find the solutions to problems that assume that form. And therefore, it follows that if we have a log to base b of 1, this is going to be equal to 0. So this stems from the fact that any number may be x raised to power 0 is equals 1. So this also is a rule that is going to apply from indices to logarithms. So suppose we have a function that is log to base b of an x. So this is going to be, remember we can write 1 over 2 as 2 raised to negative 1. So therefore, this from the indices, we can as well write this one as log to base b x negative 1. Now this negative 1 here comes from the fact that this fraction can be written as x raised to negative 1, which of course is going to be taken to be that part of that function. So therefore, a number that is appearing for this general equation, like a log to base 10 over third, is going to be negative log to base 10 3. So these three specific rules that I've listed on the board are going to be applicable. And of course, when we are going to apply these rules of logarithms, all logs must be to the same base in applying the rules that we have stated for solving for values of the unknowns like the x and y that we have written. The most common base for logarithms are the logs to the base of 10 or logs to the base e, of course, which is just right on this part. So as we have said, all logs must be to the same base for us to perform an operation and find values for the figures that are unknown. And then we have said that the most common, of course, logarithm is log to base 10. This is the most common form of logarithm that we usually use, maybe of a number x equals n. Now in this case, we're going to find this one can be written as 10n equals x as an exponential function. But if we try to look at examples like this one, log to base e. Now this case, we have said that this is also another part of our most common base that we normally use. In this case, e implies what we call a mathematical constant. Mathematical constant, which of course has got a value, which is e, just giving an approximation, but it's a large number, so e is 718,281. Now this e refers to a base of a natural logarithm, and is used in problems relating to exponential growth and decay. Of course, we're going to see in some of the processes like bacterial culture. Of course, in biology, this is a bacterial culture, trying to determine the number of bacteria that are going to be in a culture medium, or maybe in a radioactive decay, and other series which of course are going to assume that form. This natural logarithms is going to be applicable trying to solve problems relating to such a kind of equations. So in this case, we're going to give a demonstration, and for this case, log to base is referred to as natural logarithms. So for instance, if I have log to base e of x, then this one can be written as the natural logarithm of x. Therefore, log to base e's are called natural logarithms. If we have a function like y is equals the exponent of x, which is equals to natural logarithm, the exponent of x, that natural logarithm, then we are going to have, so or implying that log to base e y is equals x. So this basically is going to be the same as I've said, log to base e, this is the natural logarithm of y is equals x. So these two forms can be written in these two different ways. And of course, in case we come across them, it's going to assist us to find solutions to that. Now there's this of course case whereby, as we stated, that log to base b of x, of course, I don't know, just a minute, there's something I'm trying to illustrate for our understanding here. We said that log to base b of x is equals 0 if x is equals 1. So which implies that a number raised to power 0 is equals 1. So in this case, for these logarithms that we have said, the natural log of e is equals 1. So this is another condition that is analogous to what we have just illustrated on the board. So therefore, we are going to use those particular features and laws of logarithms to find solutions to some of the problems. There are two basic examples I'm also going to illustrate before we just tackle a sample question to assist us understand how this concept of logarithms can be used to find solutions of algebraic expressions or equations where the unknown variables appear as powers. So if we have log to base p, this is also going to give us 1, implying b raised to power 1 is equals p as an exponential function. So in this case, we can have another one, which is log to base b n the root of x. This is going to give us this one, and then log to base b x. Of course, we saw from the exponents, especially of fractions, how we can be able to interchange this one, bearing in mind that a number like this can be written as 2 that way. So in this case, this is a function, or the analogy that is being applied there. So let's look at an example whereby we have been given a function and we have been requested to find the solution to that. Now we shall be applying the rules of logarithms that we have stated to try and find the solution to that. Of course, we shall be mentioning the specific rules that we have already done. And if we have asked to find the value of x for this exponential equation, so this is just number 3, just write it properly. So this is 3 and then raised to power x. So there's an equation of this form, and we are being asked to find the solution for x. Now the first step that we are going to take is that we are going to rewrite the equation so that x is not a power by taking logarithms of both sides. So in the first step that we are going to take is to find logarithms of both sides, which is log of 5x, log to power x, and the log of 3 raised to x on both sides. So applying the rule number 1 that you had stated, that for products of this kind, then the logarithm is going to be the sum of those two, of course, parts of that product. So we have rule number 1 applied, and we write as log to 5 raised to x is equals log to 2, the first part of the product, plus log to 3x. And then applying rule number 3 that we had stated about the logarithm for exponential functions, we will write, of course, that is the first part of it on the right side, x log to 5 is equals log of 2 plus another exponent, x, the log of 3. So these ones, of course, we can just have a look and see that there are like terms on the left side and the last part of the equation. So we'll have x as a common factor, log to 5 minus log of 3 is equals log of 2. So therefore, for this case, we've talked about we talked about the third rule, which was applicable for addition and subtraction. So this part of the left side of the equation, we can write it as a fraction by writing x log to 5 over 3 is equals log 2. So therefore, making x the subject of that formula, then we shall have the log of 2 over log 5 over 3. So in this case, trying to find the values for both log 2 and log 5, that one will give us, this is to 2 decimal places, so that will be the value of x that we are trying to find in that particular equation. So in this case, we're going, this is one of the illustrations on how we can be able to use logarithms to find the unknown variables that appears as powers in such a kind of a function. So for that case, guys, that is it for today. Thank you. Bye. God bless you.